Day 6 is the binomial theorem. In this first video, all I'm going to do is expand the following binomials, and then we're going to look at that expansion to find patterns. So what you may want to do is actually pause the video at this point and do the expansions on your own, and then start the video again to see if you are getting them right. Because I'm not going to be showing my work for all of them because that would take lots of space. So a plus b to the 0 starting off, well, we know anything to the power of 0 is 1, so a plus b to the 0 is 1. A plus b all to the 1 gives us a plus b. For the purposes of today, though, I'm going to actually write this as 1a plus 1b. And we'll see why a little bit later. A plus b all squared. This is 1a squared plus 2ab plus 1b squared. For a plus b all cubed, I have 1a cubed plus 3a squared b plus 3ab squared plus 1b cubed. Next, I have 1a to the power of 4 plus 4a cubed b plus 6a squared b squared plus 4ab cubed plus 1b to the 4th. And in my last row, I have 1a to the 5 plus 5a to the power of 4b plus 10a cubed b squared plus 10a squared b cubed plus 5ab to the power of 4 plus 1b to the power of 5. So if you did your full day's homework for day 5, you may notice that this triangle looks familiar, and this triangle forms something that we call Pascal's triangle. And hopefully you did your reading and question on this in your day 5 homework. So let's take a look at some properties of this expansion. So what are the properties of binomial expansion? Well, how many terms are there when we expand? For example, if I expand a plus b all squared, how many terms do I end up with? Well, I end up with 1, 2, 3 terms. If I expand a plus b all cubed, I end up with 4 terms. So I end up with one more term than my exponent. And my exponent here is represented by n. So where my exponent is 2, I have 3 terms. When my exponent is 5, I have 6 terms. So there are always n plus 1 terms in the expansion. What about the sum of the exponents of a and b in each term? So let's take a look at that. Let's just pick the a plus b to the power of 4. The sum of the exponents in the first term is 4, right? There's only a, so it's a to the power of 4. In the second term, I have a cubed times b to the invisible 1. So the sum of the exponents, 3 plus 1, still 4. Here, 2 and 2 is 4. Here, a to the 1 plus b cubed, that gives me 4. And here I have b to the power of 4. So the sum of a and b in each term is equal to the exponent of the binomial that you started with. So the sum of a and b in each term is simply n. The exponents of, this shouldn't say the exponents of a, I'll put some quotations, So what happens to the exponents of a as we go term by term? Let's just take a look at the last row here. Here the exponent of a starts at 5, then goes to 4, 3, 2, 1, and in our last term we don't see a. Well, that's because really this is a to the power of 1. In my last term I have a to the power of 0. So there's an invisible ghost of a to the 0 in this last term here, which is equal to 1, which is why we don't see it. So what actually happens is that the exponents of a decrease by 1 term by term, starting at n, so starting at the original exponent, all the way to 0. Let's take a look at what happens to b. So b is invisible in my first term, and that's really because I have a b to the power of 0, which again is equal to 1, so it's invisible. Then I have b to the power of 1, 2, 3, 4, 5. This triangle is full of patterns. So the exponents of b increase by 1, starting at 0 and going to n. How could we describe the coefficients in this expansion? Let's take a look at the coefficients. So I'm just going to arbitrarily choose this row right here to the power of 4. So my coefficients are 1, 4, 6, 4, 1. They are symmetrical. So we can say that the coefficients in each expression form a symmetrical arrangement. The sum of the coefficients in each expansion. Okay, let's take a look at the sum of the coefficients in each expansion. Here the sum of the coefficients is 1. In the second row it's 1 and 1. Now you know why I put all those 1's in, which is 2. Here it's 1 plus 2 plus 1, which is 4. 1 plus 3 plus 3 plus 1, 8. 1 and 4 and 6 and 4 and 1, 16. 1, 5, 10, 10, 5, 1 is 32. So maybe pause it right now and see if you can find the pattern. Then you can play it back once you think you found it. So if you notice that the pattern is 2, for the sum of the coefficients is that the pattern is 2 to the power of n, which in this case would be cubed, which in this case would be 4, this case 5, you are correct. The sum of the coefficients in each expansion is 2 to the power of n. I'm going to stop the video here. I will start the next one for the next questions, but before that, why don't you try and use the pattern in this triangle to complete the following expansions rather than FOIL out however many times. And in case you haven't seen this pattern, let's use pink. Each coefficient comes from the sum of, oh whoops, I just did that upside down. Each coefficient comes from the sum of the coefficients above. So 3 is 1 plus 2, 6 is 3 and 3, 4 is 1 and 3, etc. So see if you can use the pattern with the coefficients plus what we just looked at with exponents to come up with the remaining expansions at the bottom.